Tonight, a look at a method of power generation that was once thought to be antiquated and why scientists and engineers are once again excited about this method.
So this is a very interesting project for many disciplines and many types of approaches to get this to get this to work.
I'm Adam Wilson, and this is 6 Minutes of Science. The year is 1821. Thomas Seebeck has just discovered that a circuit of two different metals at two different temperatures would deflect the compass needle. Seebeck erroneously thought that the temperature difference induced magnetism between the two metals. This was close to being correct, but was not quite correct. In actuality, current was induced from a thermoelectric force that passed between the metals, and the compass was deflected by an effect that was a consequence of what is known as Ampere's law, where a magnetic field is induced through a passing current. A few years later, in France, Jean-Charles A. Peltier independently found that current between two different metals would heat one side and cool the other. Peltier used this to freeze liquid water into ice on one side of a metal and then reversed the current and melted the water on the same metal. So we see that the thermoelectric effect goes both ways, both for power generation and to generate a temperature difference. From the time of the discovery of the thermoelectric effect and up until the 1960s, development and progress was made in the field. Niche applications were developed and exciting research continued to be done. However, these devices were highly inefficient and supplied very little electricity, so they were only used in places where they were most advantageous. During the 1960s, the limit of knowledge was reached as to what materials make good thermoelectric materials, and because of this, the efficiency of such materials was not improved from the 1960s until the 1990s. During those some 30 years in which no improvements were made, thermoelectric materials became an afterthought. Why waste focus and energy on a material that's as good as it's going to get and that it only has applications in certain key settings and in niche situations? However, that was about to change with the advent of nanotechnology.
So everybody who is doing thermoelectrics today are looking at nanostructuring because everybody's convinced that this is the way to go to achieve the lowest thermal conductivity.
In case you just missed that, what Professor Kanatsitis is saying is that the thermoelectric materials can be made more efficient with the utilization of nanotechnology. But how exactly does this improvement work? How can nanotechnology help improve the efficiency of converting heat into electricity and vice versa? To have a good understanding, we first have to have a firm grasp on what nanotechnology is.
A nanometer is 1/1000th of a meter. That's tiny. So tiny I have trouble wrapping my head around it. The head of a pin is 1 millimeter across. Divide by 10, 0.1 of a millimeter, the width of a human hair. Divide that millimeter by 100 and you get to the size of ultrafine water droplets found in fog. The smallest bacteria, hundreds of nanometers wide. Strand of DNA inside that bacterium, which houses its genetic code, is about 10 nanometers across, and a nanometer itself is less than 10 carbon atoms long. Nanotechnology is about the behavior of materials or devices at these incredibly small nanoscales. Technology somewhere between bacteria and atoms.
So the question remains, how does attention to the very small scale of the material lead to an improvement in efficiency? To understand this, we need to define a few key terms. The first of these terms is the electrical conductivity, represented by the Greek letter sigma. The electrical conductivity is essentially the propensity of the material to give or receive electrons. The next term is the thermal conductivity, represented by kappa. The thermal conductivity is the propensity of the material to absorb or emit heat. The last term is the Seebeck coefficient, represented by capital S. The Seebeck coefficient is a property of the material that says how much electricity is produced per degree of temperature difference.
Where Z including S squared sigma over K. And this is the figure of merit.
Professor Chen is showing a common reference for the efficiency of thermoelectric materials, the dimensionless figure of merit ZT, which is composed of the terms we just discussed. So, to improve the efficiency of thermoelectric materials, we have three options. Increase the Seebeck coefficient, allow electrons to travel more easily through the materials, or inhibit heat flow between the materials. This is where controlling things at the nanoscale helps us out. One of the most effective ways to do this is to stack layers of materials that are only a few atoms thick, one on top of the other. This is called a superlattice. Such materials have been shown in labs to more than double the ZT of the best devices before nanotechnology was involved. So why do we care about increasing the efficiency of these materials? What could we do with more efficient thermoelectric materials? Well, for starters, the majority of the energy coming from the sun is not absorbable by traditional solar cells. However, all of the energy from the sun goes into heating, especially when focused. This could make alternative solar energy for individual homes, even in such methods as solar paint, a feasible reality. There are other applications, such as heating and cooling without moving parts, self-powered biomedical applications. The potential uses are as many as the imagination can conjure. For 6 Minutes of Science, this is Adam Wilson. Good night.